Great. Hi, everyone. Thank you for coming back. And thanks, Andy, for coming back. Today we have Andy Manion again, who's going to tell us about higher representations and coordinated Heegaard Floer homology, part 2.
Thanks very much for coming again, and thanks to the organizers for inviting me. So I'm going to continue talking about joint work with Raphael Rouquier. And last week we talked about a tensor product operation for two representations of a certain DG monoidal category or DG2 category that we defined with pictures. And we had a version for two representations on categories by functors and natural transformations, and a version for two representations on algebras by bimodules and bimodule maps. So in this talk, what we're going to do is see this formula, well, we'll see this tensor product operation applied to give a formula that extends on a previously known formula of Douglas and Manolescu for gluing certain algebras that appear in bordered Floer homology. So we're going to start by defining those algebras, or at least giving an idea of the definition. And then we're going to discuss a little bit about cornered Floer homology and, well, at the algebraic level, and how we package that into a bunch of examples of two representations of this U from the last talk. And then we'll talk about how we build upon Douglas-Manolescu's gluing formula using these ideas. Okay, so we discussed this tensor product operation last time. And this time, right, so that's what we're going to do. We're going to have a large family of two representations and a gluing formula for them. Okay, so here's the setting. We're going to start with sort of diagrammatic input. And from that, we're going to get an output. And the diagrammatic input is going to be called a chord diagram, also known as an arc diagram. And what it is a compact oriented one manifold, Z, but it might have boundaries. So that means it's just a finite disjoint union of oriented circles and intervals. And then it's equipped with a 2-to-1 matching of finitely many points in its interior. So we draw the matched points with red arcs connecting 2 points that are matched. So we have two examples of this here. The first one has a single interval and 2 pairs of matched points. Second one has an interval and 2 circles, and same thing. And these types of diagrams were first used in Heegaard Floer by Zarev in his PhD thesis on bordered sutured Floer homology, but he didn't discuss the version with circles in them, just the version where you might have multiple intervals and then a matching on them. Okay, now if I specialize to the case of a single interval, so that's like that first example where I have a matched interval above, then these types of chord diagrams are in bijection with another sort of diagrammatic thing called pointed matched circles. I can just think of gluing the two endpoints of the interval together and putting a base point there at the glued point, or equivalently, given a pointed matched circle, I can think of cutting it open and getting an arc diagram with a single interval. So the original formulation of bordered Floer homology due to LOT use these pointed matched circles. And the chord diagrams after this translation of cutting it open, the chord diagrams are a generalization. And I guess I got the term chord diagram, especially from Bob Penner. These are studied in various fields of topology and other parts of math, especially as representations for surfaces, and that's how they're being used here. So somehow there's papers that use chord diagram in this setting, so I've started using that. But what are we going to do given a chord diagram? If Z is a chord diagram, we're going to define a Strands algebra. And this is just using the same idea of the definitions of LOT and Zarev. It's the same definition in every case. The definition makes sense even if you allow circles as well as intervals in your chord diagram, but you have to, you have to give precise definitions, and we have them in our paper. But we do, so we have algebras, Strands algebras for all chord diagram Z as defined above. One remark is that in this generality, if you start allowing circles in your chord diagrams, now if you want to do Heegaard Floer with these Strands algebras, and you want to have Heegaard diagrams giving you modules over these algebras, you may need to consider more elaborate versions. Work in preparation of LOT indicates that sometimes curved A infinity deformations are necessary. This is this bordered HF minus for torus boundary project. So with that caveat in mind, we have Strands algebras for every z. And ours is the basic thing, of which theirs is a curved A-infinity deformation in that particular case. Okay, so I want to just say a little bit about the definition of the Strands algebra A of Z. We're going to define it by, well, it's going to be an algebra over the field with two elements, and that's not just for laziness purposes, but because it's significantly more difficult to work out how signs should interact with the gradings when you're not over a field of characteristic 2. So we're going to work over F2 here. We're going to define an algebra by giving a basis over F2, and then we're going to say how to multiply. It's going to be a DG algebra. We'll give a differential. And just like last talk, we're going to say DG, but we're not actually going to discuss gradings in this talk. So DG will really mean differential. Okay, so I have to start by giving a basis, and there are these so-called Strands pictures. So I drew two examples of Strands pictures here, and a Strands picture, if I have circles in Z, then a Strands picture can look like that second thing where it can wrap around as many times as you want. And so what are these things? Well, they're pictures like the above ones, and where are they drawn? The canvas that you draw them on is just an interval times z. So that's where you would draw, for instance, graphs of paths in z, and that's what these are, collections of graphs of paths in z. You consider them up to isotopy. So if I, there's only one strand picture. If I look at this second one that is a single strand going from the bottom red point to the top, there's only one such strand picture because any such pictures are isotopic. Okay, so I'm only considering these up to isotopy. The strands must be upward veering if I draw the orientations to point upwards, which I sort of suppressed here. In general, the strands have to go in the same direction as the orientation on your Z. And then the important rule is that you don't have any double occupied matchings on the left or right. When I mean occupied, I mean if I look at those red matching arcs on the left or right of the diagram, whether or not there's a strand that comes in or not. And the only time I'm allowed to have double occupied matchings is with horizontal strands. If I have a horizontal strand, then that matching must be double occupied. I must have that other strand and it must be horizontal. So horizontal strands come in matched pairs and you draw them with dotted lines to just remember that they're special in some sense. Okay, so these sort of things are my basis. And well, okay, actually let me define the multiplication first and then I'll talk about idempotence. The multiplication is I just stack things left to right and try to line up the strands. So if I have a strand coming in this first type of picture, if the strands don't match up, if there's nothing to glue a strand on the right, if there's no strand on the left to glue to it, then the product is 0. And how do these dotted lines interact with the product? Well, if you want to multiply a dotted line by something, then that moving something is going to pick one of your two sides. It's going to end either at one or the other of your dotted lines, and then you erase the one that doesn't get used and solidify the one that does get used, and then you concatenate like normal. So that's how you deal with the dotted lines.
Okay, Andy, I have a question. Can you go back for a second to the previous slide?
Yes.
Do you have the same red diagram on the left or on the right, or different diagrams in general?
It must be the same diagram.
It's the same diagram, so it's fixed. And
yes,
then,
fixed Z.
And then the diagram consists, then in the middle you have dotted lines and you have dashed lines and you have regular blue lines.
Yep.
And then, so if a dotted line connects, dotted lines can only be horizontal.
Exactly, yes.
So
that's right.
dotted lines are upward veering. They can never be horizontal.
Right, that's right, exactly.
And then if an upward veering solid line connects one of the endpoints of a red arc, does it have to go to the same arc on the other side?
No, it can, like in this second example on this page, it goes to a different one, for instance.
So in this, okay. But so for any red arc, it must either have a, so that's.
It might be totally unoccupied.
Okay, and so there's some basic degree by the number of by the number of dashed blue lines.
Well, okay, as will it's on the next slide. So it's shown by LOT. It's actually relatively complicated. So there's if I look at this first example, where I just have the so-called torus matching on a single interval, okay? Then actually there is no, so if I just look at the sum end with one strand, it's fine. But if I look at the sum end with two strands, there's a simple argument to show that there's no Z homological grading on that algebra such that the strands pictures are homogeneous with respect to it. You'd get a contradiction if you had such a Z homological grading. So that's a sign that in terms of the degree property of these things, it's very very subtle somehow.
And that's if you have a red arc, say on the left, right, and it has a dashed line emanating from one endpoint, it has to have a dashed line emanating from the other endpoint.
Exactly. Yes.
But if it has a blue solid line emanating from endpoint, it should not have anything
Right.
emanating. And
Exactly.
the same for incoming. Same for incoming.
Yes. Exactly.
Okay.
Good. So right. So that is the algebra. Well, I should say a couple things. We have, if I just look at strands pictures where I don't have any moving strands at all I have is these dotted horizontal strands. These are all idempotent, and they, well, a pair of dotted times the same pair of dotted just gives itself back. And these form a complete set of primitive orthogonal idempotent, so they sum to one. They're multiply by 0 to each other. They can't be written as sums. And so well, those will be mentioned later in the talk, so I wanted to bring them up, but this is one picture. The differential on this algebra is you so-called resolve the crossing. So if I see a crossing, I just replace that with the other natural thing I could do where there isn't a crossing, but things are still orientation preserving. Okay, and the only subtlety there is that with these dotted lines, it's the same solidify and erase pattern. I'm going to look at, so I'm going to look at that first crossing with the top dotted line. To resolve that, what I'm going to do is first erase the other dotted line and solidify the top one, and then resolve the crossing. But I could have equally well done that for the bottom crossing with the dotted line, and that's where I'd get the sum of two things here in this differential. So this is somehow becomes complicated when you try to put in a grading, but that's just as a differential algebra. This is what it is. It has a grading by a non-abelian group in general, central extension of the first homology of the surface. So these algebras, I want to say a little bit about why you would study these algebras, why you'd expect these algebras to be important in the context of Heegaard Floer homology. And well, what does one use such a chord diagram for? A chord diagram is a representation for a surface. They're one of many different types of combinatory representations of surfaces that come up in low dimensional topology. And in particular, these most naturally represent so-called sutured surfaces. These are, well, compact surfaces with boundary, and then they have certain extra structure on the boundary. And the extra structure amounts to a boundary of the surface being divided into so-called stopped regions and unstopped regions, or you can call that S minus and S plus. These should sort of interface along the intersection between these, maybe if you want, should be a finite zero manifold that you call lambda, the set of sutures. So you have intervals or circles in S plus and S minus, and you can have like a circle in the boundary of Z being written as a bunch of S plus or S minus intervals. You can, or sorry, a circle in the boundary of the surface represented by Z. But let me say a little bit about, just draw this picture. What do I mean by the surface represented by your chord diagram? So if I have this basic interval with the torus matching like on the other page, then the surface associated to that, what I'm going to do is thicken the black part of the diagram. So thicken the intervals and circles, okay? And I'm going to then attach one handles according to the matching arcs. So that gives me just this basic outline of the picture. And now anytime I had an interval in my Z, I'm at the two endpoints of that interval. Those now become little tiny little intervals, and I'm going to put a suture in the middle of each one. And the sort of half of the this little rectangle I got from the interval, the half where I didn't glue the one handles, that becomes S plus, the unstopped boundary, okay? And if I had as in this second picture, if I had a circle rather than an interval in Z, then that would thicken out to a little annulus. And then the side of that annulus where I didn't glue the one handles would be an S plus, the unstopped boundary. And then all of the rest of the boundary is in S minus, the stopped boundary. Explain that a little bit in a second. And then what I'm drawing is inside the surface that you get, your chord diagram can naturally be drawn as a family of arcs in the surface. So I'm drawing those in red. S plus I'm drawing in orange, S minus in black, the little lambda points I'm drawing in green. So hopefully, well, one of those pictures is relatively small, but hopefully this is sensible. So the Z represents surface with this amount of extra data. And you can think of the red arcs as being, that's your choice, like Z is somehow a choice of triangulation. And the red arcs are your choice. But you want to think of the rest of the structure as really being intrinsically part of the sutured surface data, okay? And so what does the sutured structure do for you? It lets you define partially wrapped Fukaya categories, and Aru has shown that these Strands algebras, they're an explicit description of partially wrapped Fukaya categories of the following sort of thing. I take a surface F, and let's assume it has this sutured structure. And then I take a k-fold symmetric power of it for various k. And I can then look at partially wrapped Fukaya categories of such things where to define partially wrapped Fukaya category, I have to say, how am I wrapping? Are there stops or something? And that comes from the sutured structure on the surface. And so that's what these algebras are doing. They're describing these Fukaya categories. And this is something that a priori should be related to Heegaard Floer homology. From the basic definitions of Heegaard Floer homology, it was an approach to Seiberg-Witten theory that sort of took as an ansatz that it assigns to a surface some Fukaya category of a symmetric power of that surface. And then you apply that idea to Heegaard decompositions, and that sort of gives out the original definitions of Heegaard Floer homology. So at least it's plausible that, if these A of Z's are describing partially wrapped Fukaya categories of sutured surfaces, that's at least close enough to, for instance, the original definitions of Heegaard Floer. You should expect that these are very natural things to consider in bordered Floer homology. Just want to make one remark relevant to this project on why does one use sutured surfaces and correspondingly partially wrapped Fukaya categories. That's not something you immediately see from the original definitions of Heegaard Floer homology. There's a couple views you could take on this. One view, popular among many, is that this is a sign that Heegaard Floer is really not a TQFT in the sense that people do axiomatic TQFTs, that it's somehow defined that it's not something that's just associated to plain old manifolds, that it's associated to manifolds with some extra decoration structure, and you take this suture structure to be something different, something more geometric that isn't really what you see if you're doing a TIA or Lurie or something style TQFT. And so then you say, well, we'll study this theory as it is, see what properties it satisfies rather than trying to shoehorn it into another framework. So that's one view. A related view is that, well, maybe you like this TQFT framework, but then you still think, well, the sutures don't look good from that framework. They sort of look like this extra junk on your surface. And so you're going to try to hide the sutures. And then you might prefer working with pointed match circles, viewing them as representing closed surfaces. And then you accept the penalty that you must, not have a TQFT, or at least for plain manifolds still, but for like surfaces with base point, 3 manifolds with base point, 4 manifolds with embedded graphs. This is another perspective that some people take. I am going to suggest that there is yet another perspective. So these perspectives have something in common where the sutures are viewed as something contrary to TQFT for plain manifolds, okay? That the sutures are something different or weird than the usual theory of extended TQFT. And a point of view that's sort of suggested by this project is that there's another way to view it, that perhaps the sutured structure is very natural from the point of view of just plain manifolds TQFT. That when you're doing extended TQFT in the most standard settings, you are still looking at not necessarily just plain manifolds, but manifolds with corners, plain manifolds with corners if you want, and your things are associated to that. Your sutured structure looks a little bit like a manifold with corner structure. On a surface, you can think of your lambda as corner points and having angles between your S plus and S minus boundary. So you could wonder, is there some viewpoint on Heegaard Floer homology where it is really associated to plane manifolds? Not really base point decorations or more drastic sorts of decorations, but really just to plane manifolds. And well, you'd be thinking of the sutured structure as just the structure of being a morphism in a higher cobordism category. And so that's suggested by this project, although there's a lot to work out. This is a sort of less standard perspective that I'm hoping it's something that can become realized as we go on, partially as a result of work of this project. But just one thing to note is that that would involve an extension down to points because the sutured surface would have zero-dimensional corners. So I'll say a little bit about that at the very end of the talk. But what I want to do is, okay, there we go. So what we're going to do is discuss the actual constructions and results of this paper having to do with Strands algebras. And the first thing we're going to focus on is talking about how we get examples of two representations of U on these algebras. So what's really going to be the case is that I have this chord diagram. It's made up of circles and intervals. Well, the circles we're not going to have two actions for. But for each interval, we're going to have a two action of this U, A of Z comma E tau. So we'll be able to upgrade A of Z into this two representation data by defining E and tau. And it's going to be a reformulation of work of Douglas-Manolescu in Chord Floer homology. So we're going to take the pictures that they drew and repackage them to define this E tau data. And so I guess we're going to start by saying a little bit about how they view it and how our perspective is slightly different. So the question they started with in the framework of pointed match circles, which was, if I have one of these, it looks like I can cut this in the middle, sort of through the base point and between the two sets of matchings. And then I get these two pieces that I draw. And you can ask, well, can I recover the algebra of the glued thing from some data associated to the pieces? And their answer goes as follows. To the top piece, I'm going to associate something built from pictures like this first little strands picture I drew, where you have strands that emerge from the bottom. Okay, it's like a cut in where this how the strands pictures would be, and then associated to the bottom piece, I would have some gadget built from strands pictures like the second one, where strands leave to the top. Okay, as you're going left to right, and then their formula will say that the algebra for the glued together diagram, I can write it as a direct sum. If any strands picture for the glued together diagram, that's going to have a certain number of strands crossing through this interface between the two pieces, okay? These have to be moving strands, right? Because horizontal strands can't ever cross this horizontal interface, right? So it's just a certain well-defined number of solid moving strands, call that M, and then your strands picture for the glued diagram can be viewed as a top piece glued with a bottom piece. The top piece is an element of this whatever algebraic gadget is associated to the top half of the pointed match circle. And similarly for this bottom piece. And then you're allowed to, for instance, if I were to, in these two strands pictures I drew, if I took the left one and stacked it on top of the right one, okay, then that looks like it would give me a strands picture in the glued diagram, and it has a crossing sort of above the interface. But equally well, I could isotope that crossing to be below the interface, and that's why I'm tensor over this thing called HM here. HM was just the, this nil-Coxeter algebra, this endomorphisms of e to the m in the DG monoidal category U. So it's just generated by the black crossing tau with the usual relations. And so that acts on strands pictures of this form by sort of plugging in the tau picture, the nil-Coxeter picture, sort of concatenating that on bottom of these type of strands pictures or on top. Okay, so this is just an illustration of a strands picture for the glued thing viewed as being built from these two types of pictures. Okay, so and if you're remembering from this last talk, this sort of direct sum over M formula looks familiar. That's one way of, well, there was a formulation of the tensor product that looked quite a bit like that. Okay, so now in our perspective, we'll be following Zarev rather than pointed match circles because that's, we'll see exactly why that's appropriate for this project. So in the previous setting, we wouldn't be trying to get a pointed match circle from two pieces that look a little bit weirder. We would instead be trying to get this matched interval from two pieces that are themselves matched intervals. Okay, and so we're going to say that this extra data that was associated to the top and bottom halves in the previous picture, that's going to become the two representation data, E and tau, on each of these pieces. And then because the new glued picture is itself still an interval, it still has an E and a tau itself. Whereas in the pointed match circles formulation, it didn't seem like it should have the same type of structures that the two pieces had. So that's a difference between this perspective, between these two perspectives. If we see, and we will, that the result of gluing is something which itself naturally carries this higher action, that indicates we should be doing the Zarev version rather than the pointed match circle version. So how are we going to, so if we have one of these chord diagrams with a distinguished interval, we're going to, well, we'll use the pictures where one strand leaves upward, a single strand leaving upward, and we're going to take such pictures as an F2 basis for a bimodule over the algebra A of Z. Okay, and well, what are the bimodule actions? I just multiply by concatenating, just like I would in the strands algebra. It doesn't really matter that a strand leaves to the top. If it leaves to the top and then I act with an algebra element on the left, then in the result, the strand will still leave to the top. So I get an element of this bimodule E still, same for the right action. Differential is resolving crossings. And so one thing, if you remember from last talk, that we needed to take these tensor products in this algebra setting is we needed a left adjoint for our bimodule E. And here, well, what I'm going to argue briefly for is that actually E is finitely generated and projective as a right module, at least if you ignore the differential. And so it's very simple to get, I can just take the right dual. When I write hom over A of Z up, that means hom as right modules over A of Z. That's Raphael's preferred notation for that. That produces a left adjoint bimodule, but I can think of that much more geometrically. So why is this finitely generated and projective as a right module? Well, I claim that if I ignore the differential, then it's a finite direct sum of the following type of modules, just one of these primitive idempotents times the algebra on the right. Okay, so these are sort of basic projective right modules, and I'm claiming E is a direct sum of those, where the summands correspond to following type of strands pictures. One strand leaves to the top, no other strands move at all. Okay, so those type of pictures, I claim it's anything in E can be uniquely written as one of those type of pictures times an algebra element on the right, with compatible idempotent in between. And the reason is if I just have any strands picture in E that has some strand leaving to the top, but I can just isotope that so it immediately leaves to the top before anything else moves. Okay, it's not going to create any problems doing this. It sort of gets out of the way, so it's not going to interfere with where the other strands need to go. And there's no way to build a double crossing by doing this type of isotopy. So you can always, so this is a geometric argument why E decomposes as a direct sum of such things parameterized by these special types of strands pictures. So if I have a strands picture like this, then I'm saying that gives you a summand I dot A of Z for some idempotent I. And which one? Well, I'm just going to look at the occupancy on the right side of my basic strands picture. And I didn't really draw these red arcs, but let's assume they're there. I'm going to look at which red arcs are occupied on the right versus not occupied on the right. That gives me my idempotent I. Okay, so that is one way to think about E, and then you can immediately tell what the dual is going to be. If I take hom of right modules from such a thing into the algebra itself, basically it's just going to be another finite direct sum of projective left modules now. And parameterized by the same stuff, but now the algebra element will be on the left. So that's one way to think about this dual. A more geometric way is that, in fact, this left dual or this left adjoint right dual thing also has strands pictures. It's the other type from Douglas-Manolescu. It's the type where one strand emerges from the bottom. Okay, I claim that this set of pictures used as the basis for a bimodule as usual. This gives the bimodule that is the left adjoint or right dual to E. So if I define a bimodule like this, then I can just say sort of the strand emerges at the very end after everything has moved. And so I can factor everything as algebra element times basic strands generator. And this thing as defined is just like the dual of E. It's a finite direct sum of A of Z times idempotent. And now I can think of the summands as being parameterized by these basic one strand emerging things where you have, again, one strand emerges from the bottom, but no other strands move at all. And then that times an algebra element on the left, that will give you a general element of this geometric bimodule. Now, right, so the idempotent then that corresponds to it is the occupied matchings on the left rather than the right now. And so here, yes.
When you say that no other strands move, you really mean that all the remaining strands are dashed blue.
Yes, exactly. Exactly. Yes.
Thank you.
Yep. So I said that somehow that these pictures are dual to the other pictures, and actually it's, you know, very concrete how that works. These types of pictures line up with the other ones, and there's a pairing. And actually, next slide we'll talk about a unit and co-unit. But just as a first example, this picture here, it has one strand emerging and it ends at a certain point. That's dual to the one where the strand starts at exactly that point and then leaves. Okay, so each picture for E has exactly one corresponding picture for this E dual thing. So we're going to be identifying these two perspectives. And just to be especially clear about that, you can think in terms of a unit and co-unit. And this is sort of compatible with this strands picture or string picture way we were drawing last time. So we're saying E check is a left adjoint to E. So the unit should go from identity to right adjoint times left adjoint. And the identity bimodule, that you can think of that as just the same strands pictures as the algebra itself. And how is the unit going to act? Well, it sort of adds an imaginary vertical line, actually wherever you want. Let's say I add this vertical line here, and then I resolve crossings with that vertical line and view the results as being in E tensor E check. And that's well defined. One can show that that's a, you know, this sort of procedure gives a well-defined element of E tensor E check. Here's one example. So I get a term and then another term that's 0. It actually doesn't matter where on the left and right I put this vertical line. Let's say I put it over here, then I'm going to get these two pictures. The second one is the same as this first picture on the previous slide. So that's how this unit of the adjunction between these two geometric bimodules works in terms of strands. The co-unit is basically this duality pairing that we had before. Okay, so it's on E dual tensor E, that's sort of projective on the left, tensor projective on the right. So I can think of a generator of E dual tensor E as just being a pair of these basic generators for the bimodules, where just like in this picture I drew over here, you have one strand emerging, one strand leaving, and no other strands move. And then I just pair them, just like if they're dual in the sense from this slide, then epsilon sends them to, I just concatenate and remove that strand that goes through. Otherwise, epsilon sends them to 0. So that is the co-unit of the adjunction, and this is the unit, and one can check that the triangle identities are satisfied. So these are just taking a single, a single strand going up, a single strand emerging from the bottom. But how about the more general pictures from Douglas-Manolescu? That's what you get when you take tensor products of these bimodules with themselves. So E to the M, E dual to the M. Those are the sort of things from the tensor product formula or the gluing formula. And so, well, I can again describe these in terms of strands pictures. E to the M just means instead of just having one strand go up, I'm going to have M strands go up, and one can prove that. And E dual to the M, it's similar, but and there's a typo in this. I should say e to the m, not e, has a basis of these strands pictures, okay? E tensor dot 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 tensor e, m times is a basis of such strands pictures, similarly for e check. And well, why is that true? It's, if I have e tensor dot 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 tensor e, take an element in that first tensor factor, write that as like basic generator of e times algebra element, and just pass that algebra element to the right, and then just keep doing that, and you can write your element of e as something where m strands leave to the top first, and then some algebra element happens, and that's the same as this geometric bimodule. And similarly for e dual. So that's where we see this multiple number of leaving strands is just tensor powers of these things. Okay, so in particular, if I take e tensor e, then that's going to be the bimodules with 2 strands leaving to the top. And now I have this little psi or n equals 2 nil-Coxeter algebra with just generators 1 and tau that I can act on top. And that tau, that crossing, just acts by stacking a crossing on top of the strands picture. So it sends this first strands picture to the one with the crossing. Then the second one already has a crossing. I do another one that's a double crossing, and those are 0. That's maybe something that I should have said in the definition of the algebra, is that when you're multiplying, when you're doing this concatenation, it's possible that you may form a double crossing in the result. Then instead of isotoping that away, you're supposed to declare the result to be the result of that multiplication. If a double crossing would have been produced, you declare that result to be 0. Okay, and that's very much like the tau squared equals 0 relation in this U. Okay, so this is the E and the tau I get for if I have a chord diagram with a chosen interval component, then I get this E and tau, and you can check that this gives you a valid 2 representation of U. Really, this R3 move relation is just stacking on something that looks like an R3 move. These 2 sides are isotopic to each other. So that's how we repackage these Douglas-Manolescu pictures into a slightly different or related but slightly different type of algebraic gadget, this 2 representation data. Okay, and it's so this 2 representation of U, and even of this U bar version from the last talk where we assumed we had these left adjoints, we get these for any chord diagram with the chosen interval component. So let's say we have 2 of these then. Let's suppose we have Z1 and Z2, and we pick an interval in Z1 and an interval in Z2. And then, well, so we have 2 representation of U bar for the first one and the second one, but on the tensor product, then I sort of get this data of 2 commuting actions of U bar, which we viewed as an action of this U bar squared thing. And let's be a little bit specific about this. How do I get, so I'm going to use the script e's in this talk to denote bimodules over this tensor product algebra, okay? Whereas Roman E1 and E2 will just denote the bimodules over A of Z1 and A of Z2 respectively. And your script E1, the bimodule over the tensor product, will just be a Roman E1 tensor with, I guess, the identity over A of Z2. And similarly for script E2 is A of Z1 tensor with Roman E2. This script E1 bimodule over the tensor product also has a left adjoint that's just given by left adjoint of Roman E1 and then tensor with the identity on A of Z2. So that's my 2 colors of strands. E1 would be like a red strand pointing upwards. E2 would be a blue strand pointing upwards. E1 would be a red strand pointing downwards. I don't really need a blue strand pointing downwards. I would have it if, I have it from this construction, but I don't need to talk about it. And then the remaining data for this 2 action of U bar squared was this sigma isomorphism, and then that needed to have a dual lambda. Well, that by the setup has a dual lambda, and that lambda also has to be invertible. And in both of these cases, if I take like script E2, script E1, what that's going to be is just Roman E1 tensor Roman E2. And same for the other order. Script E1, script E2 is just the same thing, and there's a natural isomorphism. Take that to be sigma. Okay. Similarly, what that gives you is a certain lambda, which amounts to the following thing that just is another. If I take script E1 check tensor with E2, then that's just going to give me Roman E1 check tensor E2. And same with the other order, because these are sort of acting on different factors. So this lambda that I get is also just the natural swap map. So that's also an isomorphism. So that means this data is something to which I can apply this delta sigma, this diagonal action construction, and get a tensor product. I mean, we always had that when we had, you know, this is just a review of what we were saying last time, is that we have this two representation of u bar squared on the tensor product algebra if we have two representations on the two factors. But I just want to emphasize that this is what we're going to use to build, because this is sort of going to, I'm going to try to sketch a little bit of a proof of a theorem in a little bit, and this is going to come into it. So if I want to view a generator of this script E1, it'll be like a picture on the left where I have a generator of Roman E1 on top, and then just identity over A of Z2 on the bottom. Script E2 is similar, except it's E2 on the bottom and A of Z1 on top. E1 check is similar, E1 check on top and A of Z2 on bottom. Okay, then what does this map sigma do in terms of strands pictures? This is the sigma that would be like a blue strand on the left, red strand on the right, and then they cross. Okay, that sigma in strands pictures just looks like I start with something where you know, the moving strand happens first on bottom, and then the leaving strand happens on bottom and then on top, and I just swap it around so that the leaving strand happens on top and then on bottom. And this is a well-defined thing one can show. And similarly for this lambda, it's just swapping, okay, like this top piece versus the bottom piece, which of them I do first in a left to right manner. So this is how these sigma and lambda act. This will come up in this proof, but I think for purposes of time, I think maybe the details of the proof will be best understood by a perusal of the slides after the talk. So I'm not going to feel so bad about clicking through some certain things and not really explaining every single picture. But so because we have this 2 action of u bar squared, it makes sense to take the tensor product, and then one has a formula for that that looks exactly like Douglas-Manolescu's formula. So as a result, one can phrase Douglas-Manolescu's result as follows. So if I have Zi, Z1 and Z2 that, well, if to strictly capture their result, they would be the ones that come from pointed match circles. So they would be these single interval chord diagrams. And then if I glue them end to end to make another single interval chord diagram, like in those pictures we showed, then their result says that the algebra of the glued thing is a tensor product of the algebra of the two factors, and that's as DG algebras. And from, you know, from the perspective of this paper, it was actually viewed as pointed match circles being glued from halves of such things. And so then it didn't really seem like there's more structure to consider on the glued thing because of what we talked about before. So our version of this theorem, well, okay, one part of this isn't so bad. It's the idea is immediately generalized to Z that have arbitrary number of intervals and circles, and you just have a distinguished interval on each one you glue. Distinguished interval of Z1 to distinguished interval of Z2 to get a new chord diagram Z that has a new distinguished interval, the gluing of the previous ones. And so it's a straightforward generalization of their result to say A of Z is the tensor product of A of Z1 and A of Z2 as algebras in this case. But really what we're saying is not just as algebras, but as two representations of U. So that on this tensor product, we have an E bimodule and a tau endomorphism of E squared. On the strands picture, because we're doing the Zarev perspective, we also have that same data, and those pieces of data agree. And I just want to mention, because this actually took a large amount of time and effort and is considerably difficult somehow, there's a version of this that does sort of self-gluings of intervals. Rather than interval glued to another interval end to end, it's going to be the two ends of one interval glued to each other to make a circle in the arc diagram. That type of gluing is difficult to analyze, but we dealt with it in terms of a sort of lax version of this delta sigma construction. So that is, if you read our paper, it will sort of maybe even start with that, and then it'll discuss these stricter versions of delta sigma when we actually have the commutativity and, you know, the stricter things, the nicer properties, but this lax version gives us a self-gluing version. Okay, so I want to, maybe in 10 minutes, I want to try to summarize by pictorial example. I want to summarize why the E and tau agree on both sides. And we're going to use this example where we have interval with torus matching being glued to interval with torus matching. Okay, and so all my pictures are going to be for that example. And so I want to, so this first type of picture, and then in the final 5 minutes or so, I just want to speculate about a few things. Okay, so in this first picture just illustrates why we have DG algebras that agree on both sides. The DG algebra for the glued diagram has a basis of Strands pictures that are, like we said before, they're pictures that are glued from picture on the top, picture at the bottom. And the only thing you really need to mod out by is allowing crossings to pass from bottom to top or top to bottom. That's why you take this tensor over HM. Okay, so that illustrates Douglas-Manolescu's results, which is already familiar from their papers. I want to focus on the new stuff. So I want to, we have this script E bimodule. Let's use this notation. Let script E be the bimodule that's built abstractly over the tensor product, mapping cone of pi type of bimodule. And I want to contrast that, compare with E, the Strands bimodule over the glued together diagram. Okay, and let's remember what the script E is. This was somehow rushed over a little bit at the end last time, but script E is going to be, if I have this higher tensor product, A of Z double tensor with A of Z2, I view that as a module over itself. That, well, any module over that thing amounts to some m comma pi, where m is just the thing, but viewed as a left module over the ordinary tensor product, and pi is this map from E2 of it, E2 of m to E1 of m. Okay, so here we have E2 of this m, this identity, this algebra is a module over itself, and a map pi from that to E1 of m, and well, what was, okay, so hopefully this picture isn't so small. So in this setting, in terms of strands, we naturally know how to multiply strands algebra elements. That sort of gives me this map like zeta. So in the previous, from the previous talk, this sort of action map, how would I view that as pi? I'm supposed to dualize that and take the E1 factor over to the right. Well, it would be a picture like this, where you see that little cup that corresponds to a unit. And then, so that, use the co-unit and unit in the end to dualize maps. So this is what I mean by the pi, where that zeta is really just multiplication of something in E1 dual, something in E2. Those get viewed as an algebra element in the tensor product and multiply onto the tensor product, okay? That's what that zeta is. So this whole diagram is pi. And so what is this in Strands interpretation? Let's suppose we have something, so pi is supposed to start with something in script E2 times something in the tensor product algebra. So that's what I have here. And the first thing I'm supposed to do is apply eta. So if you, follow how eta was defined by adding the imaginary strand and resolving, you get two options for eta here, and one of them is going to eventually contribute to 0, but this top one is going to be okay. So that's if I do just this bottom piece of the string picture where I just do the red cup. And now I'm going to do the next piece where I do that zeta with the left thing unchanged. So I have this E1 check E2, and then the final element in the tensor product algebra. So this E1 check, and then E2, and then tensor stuff. And so I want to view the E1 check E2 as being an element of the tensor product algebra, and then I want to multiply here, and that will give me this picture. Okay. And so this is where this map pi, on which the cone of pi is the bimodule script E, okay? And pi acts on this picture here by sending it to this picture down here, and the other term is 0, okay? So, and even if we don't entirely remember what those pictures look like on the next page, both of these, so these are these two ones that I drew on the left here, and so what's going on is this, your bimodule Roman E, the Strands one, also comes into two parts, okay? You can have Strands pictures that go all the way down to where the, okay, this, I want to view it as coming from the left, I guess. So you can have strands pictures where your leaving strand starts in the bottom piece of the diagram and then leaves by crossing the whole top piece. Okay. Or you can also have pictures where your leaving strand just starts and lives its whole life in the top piece of the diagram. Okay. And what I'm saying is that these correspond to the two pieces of the cone of pi. The cone of pi had these two pieces. It was like this E2 tensor blah, 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 plus E1 tensor blah, 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 with an extra differential between them given by pi. And I'm saying the pieces that are, the E2 tensor blah, blah, blah corresponds to those generators of Roman E where the emerging or the leaving strand starts at the bottom piece. And the generators of E1 tensor blah, blah, blah are those generators of Roman E where the leaving strand starts on top. Okay, and how am I going to view them? I just sort of, for the bottom pictures here, it's very clear how I view, this map, how I translate between the two sides of this left-right arrow that I have. On the top, what's going on is that if I have something in E2 tensor, blah, 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 I want to view that as an actual strands element in Roman E. What I'm going to do is extend up that little leaving strand that leaves on the bottom piece. I'm going to sort of extend that all the way up to the top piece in the picture on the right side. Okay, so that is that's the only place actually where the crossings in these left pictures are going, and possible resolutions of these crossings are going to differ from crossings in the right pictures. The right picture, that topmost crossing in the top right picture, this one right here, this is the only crossing in these rightmost pictures that doesn't appear in the leftmost pictures, okay? So what we should think is that Roman E is like the direct sum of these script E2 tensor blah, 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 and script E1 tensor blah, 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 but with one extra piece of the differential. And what we saw is that, well, if I mean, on the previous slide, this is a proof by example, so it suffices to show it in this one case, I guess. In the previous slide, we saw that the map pi sent this one here, okay, to the one below it. Okay, that's how pi acted. But how does this extra component of the differential in Roman E act? It's going to resolve crossings, and it is indeed going to send this one down to this one. So all this is to say that the differentials, including the piece that comes from the mapping cone, they agree on both sides, so that script E and Roman E are the same, at least as bimodules over, well, bimodule over the higher tensor product on the right, that's pretty clear. Bimodule over the ordinary tensor product on the left is pretty clear. The main remaining difficult thing is to match the left action. And this is where some pictures come into play, especially. So I really won't, I'll probably just be able to click through and talk a little bit about some of these pictures. But remember how on this script E, this left action of the higher tensor product algebra was something defined by a 2x2 matrix. And what I wrote out in diagrams is just 2 out of the 3 entries, and the third is similar. So, okay, can I make some sense of this? Is this, so let's first look at how it goes on the, how this higher tensor product algebra acts on the Strands Roman E bimodule, okay? And I just drew 2 examples of this. This is just your standard concatenation action of the algebra on one of these bimodules, okay? And I want to, so now each of these pictures, I should be able to go and translate the pictures that are labeled A1 tensor A2 with only one strand going through. I should be able to separate that out into like E1 dual E2, script E1 dual script E2. And then for E here, this should be like script E1 and then the algebra. And now I'm going to have to that, I'm going to look at the bottom right entry of this matrix, for instance. I'm going to start applying maps to that. I'm going to first do this sigma map on the middle 2 factors, and I know how that works in Strands. And then I'm going to do a map that I should have discussed last time called a row. It's basically like another sigma or lambda type thing, also related to tau. And then I'm going to do the multiplication, because that's what this picture right here, if you can see where my little hand is hovering, That's what this picture is telling me to do, and that's very fast, but I'm 5 minutes left. So, okay, so I claim that if I just look at number 1 here, that first picture in number 1, that A1 tensor A2 picture is going to expand out as these first 2 pictures in the top row there. Okay, the second picture in row 1 here, labeled E, is going to expand out as these. Okay, I'm pointing at my computer screen. It's not very useful. These ones. Um, this bit comes from the E picture. These two come from the A1 tensor A2 factor. Okay, so now I'm going to start applying maps that come from this entry right here. First map is going to be a sigma on the middle 2 of the 4 factors. So when I do identity tensor sigma tensor identity, sigma just does this swap things, swap the order in which these things are happening. And so I'm going to get this picture here. And now I have this sort of row thing, which you're going to have to believe me, just acts like a lambda would basically, or something like that. It's going to, well, kind of, except it's 2 strands on the same piece. So what this row is going to do in this case is just pull through. It's going to take these 2 pictures and it's going to, pull the top one to the left and the bottom one to the right so that we get these 2 pictures. What's going on? Okay. And then finally, okay, so that was that. If I'm looking at this picture here, that was the first crossing between blue and red, and then the second crossing between red down and red up, and then we have a multiplication, this zeta thing. So what does that look like? That looks like I leave this leftmost strands picture unchanged, but now here I view these 2 things as an algebra element, and then I multiply that on with this algebra element, and I get this. And that's exactly the result of what we got if we just took the action on the Roman version, the Strands version of E. Okay, so this term of the action agrees, and for item 2, it's similar. I mean, here we're looking at this top right entry of the matrix. We just have sigma and then an epsilon. And so if I draw what it looks like on pictures, I do a sigma to the middle 2 here, and then I do an epsilon to the left 2. Note that if I do epsilon to these things, epsilon works via this duality business, and these things are dual to each other. And so epsilon on the left 2 factors here is basically just going to erase these factors. And this is, again, that's the element I wanted to get. That's the element that corresponded to this one down here in item 2. Okay, so that is most of the proof. How about tau? I mean, there's maybe one interesting part of tau. It's less involved than the other thing. The thing I just did is probably the most involved part of the proof, but the tau also agrees. So in the last couple seconds, I just want to say, okay, how do you view this in terms of sutured surfaces? You might have to go look at the slides for this because I won't have some. But I just want to posit 3 different ways of viewing this end-to-end gluing. These are all just, I mean, at this level of saying things, it's clear these are just topological ways of viewing the result on sutured surfaces of the end-to-end gluing we're doing on chord diagrams. And items 2 and 3 are especially related in some sense if you think about open-closed TQFT and how they relate to fully extended TQFT. You sort of interpret pictures like 3 in terms of pictures like 2. So these are very closely related to each other. But this open pair of pants gluing is especially suggestive because in a lot of situations that are more familiar, you'll associate something like, well, something related to a full quantum group and not a positive half of the quantum group to a circle. And then the sort of Hopf algebraic tensor product of representations of that quantum group will be interpreted in terms of gluing into a closed pair of pants. Here we see gluing into an open pair of pants, and it's the positive half of GL11. These are related, although making this precise is still work in progress. But we're seeing the positive half of GL11, not the full GL11, and that corresponds to the fact that our 2 actions come from intervals. We don't have anything like a full action of the GL11 for circles. That's something it's not clear where that would come from yet. Maybe you would need larger algebras. Wanted to make one remark, but I think I won't make it, just saying that I have some work in progress on something related to both this and the social subabordered HFK. But I said the last thing I want to say is just I did mention something about some guess, some speculation about Heegaard Floer extended down to a point. And here's the guess. This is just a very first level, you know, this guess cannot be the final answer. There are known reasons why this is too naive to be the final answer, but this is hopefully at least getting closer to the right ballpark. If you wanted a perspective on Heegaard Floer homology that viewed it as invariance for just plain manifolds, okay? You could say something like you have a two category of two representations of this U, this monoidal structure, the key thing that we define in this paper, allows you to view it not just as a two category, but as a three category with one object in general, like a monoidal category is a two category with one object. And that's the guess. I mean, that seems to be, at least at a first order approximation, consistent with the things that we do to say that that gets assigned to a point. Okay, now the real answer, if it exists, first of all, it's clear it's by known results that Heegaard Floer cannot be like a fully extended TQFT subject to the cobordism hypothesis, but that's still not to say that it's not interesting to assign something to a point. It may very well be interesting to assign something to a point. It's just there's known no-go results about certain aspects of the structure. So it won't be a fully defined, fully extended TQFT, but maybe it does assign something to a point. And this isn't something I've seen much speculation about, but this is our speculation, is that this three category gets assigned to a point, and that's sort of inspired by thinking about the gluing operations on surfaces that we were talking about before. So that is all. I'm sorry for going a couple minutes over. Thank you very much for your time, and thanks again for the invitation.
Thanks, Andy. Yeah, let's thank our speaker first. Thank you very much. And yeah, does anyone have any questions?
Andy, what was the difference between stopped and unstopped?
Oh,
Or-
okay. Well, in terms of what? In terms of how it interacts with the wrappings and stuff?
Why do you make this distinction? Like in Sutured Floer homology usually does no distinction. There's R minus and R plus, and they play the same role.
Well, there's S minus and S plus in the sutured surfaces. So R minus and R plus are usually names for parts of the boundary of a sutured three manifold, right?
Uh-huh.
And you can similarly give names to parts of the boundary of a sutured surface. And this is also in Zarev's bordered sutured Floer, but not in like Juha's ordinary sutured Floer. But now in the Zarev theory, he gives these, just like it's R plus R minus gamma in the ordinary sutured theory, the analogous names chosen for sutured surfaces are, I guess, S plus, S minus, and lambda. So this data, that is, it's very much like implicit in this work of Aru that's how you actually relate to, well, one, it's what's used in bordered sutured Floer homology in this setup, but even if you don't like believe that as an explanation for why this is especially important, it's that's what these algebras are describing. I mean, it describes the sort of this sutured structure, gives you the stops for the wrapping in the partially wrapped Fukaya category. I don't know if that's
No, I
quite what
didn't
you're asking. What are
go back one page, one more page.
one more page? This one?
Or two more. Okay. Sorry, I think the other direction, like lower numbers of pages.
This one?
Yes.
Or
S plus and S minus, yeah.
okay, good, yes.
So do they play different roles, the stopped and unstopped?
Yes. Well, in the Fukaya category, they do. In terms of these, in terms of the diagram, yeah, they're not really symmetric. If I want, so say there's a symmetry on sutured surfaces that interchanges S plus and S minus.
Right.
You can ask, what is that symmetry on the level of chord diagrams? That's this, oh, it's called Z to Z star in this LOT paper on Heegaard Floer homology as morphism spaces, where it's I do surgery on all the red arcs and add in as new red arcs the co-cores of all of the surgery one handles. And that's, I mean, it's not really a trivial operation going back and forth between chord diagram. So the point is that the red arcs in your arc parameterization that you draw inside the sutured surface, those must end on S plus boundary, not S minus. So there's an asymmetry in the definitions there.
Oh, I see. And your gluing theorem is just gluing along one kind of surface of regions, or?
You can think of it that way. Yeah, you're gluing, well, but not along. One thing that would be actually significantly more difficult is having really a chord diagram based understanding of what happens when I glue an orange interval in, S plus in some surface to same thing in another surface. I just glue them up. So now I have black, black. Well, if you think of like chord diagram representatives and trying to get a chord diagram representative for the glued thing already, this seems like a very subtle type of thing where you're going to have to make some choices. It's not entirely clear what's the right way of doing that. And algebraically, it might be even a little bit better, but topologically, it's not entirely clear to me how to. So even though we use this type of picture to, this when talking about the open pair of pants gluing, that's topologically equivalent, but we're not claiming to be able to define this gluing along an orange interval in general. What we can glue along are well, a couple different ways of viewing it. This is a slide that was rushed. So the first type is I just have a suture. Well, it's really gluing a suture to a suture. So if I want to expand my little green suture points out into intervals, then I'm going to glue one of those in one diagram to one of those in another diagram. I can view this in item 1 here as sort of a special case of the Honda-Kazaz-Matic gluings of sutured surfaces, where you're going to glue along some interval that, rather than the interval being like precisely one of the orange or black ones, it will sort of interleave. It'll have endpoints that are in the interiors of the orange or black parts. So if I just have a little interval that just contains the suture and a little bit of orange on top, a little bit of black on the right, and same thing on this other picture, and I glue those together Honda-Kazaz-Matic style, that's the first type of gluing. But that's the same thing as item 2, which in turn amounts to the same thing as in item 3, although that's a little bit less direct.
Okay, thanks.
Hi, Andy. Maybe a question about your speculation at the end. I think
Yep.
I'd expected you to say something involving a square root of u, but you just referred to 2 reps of u. Can you comment
U is
about
already
what
the
I'm?
square root.
U is already the square root.
Like we only
Oh, of
had
course.
E
Okay,
and we never had,
perfect. Okay, thank you.
So this is one thing that would be good to understand better is sort of the relationship between Turayev-Vero style theories associated to positive halves and whether there's some way to understand something associated to the, the full quantum group isn't really the Drinfeld double of its positive half, but if you set things up in some appropriately relative sense, then it kind of is. So that's the sort of questions that I have when trying to think about this in TQFT language. That if you don't look at the quantum version, if you don't do gradings on the categorification, you're just looking at U of GL11 plus, then you can look at the Drinfeld double of U of GL11 plus. That's a very natural thing to consider in this situation. And so that's one thing you can say. That's all very toy model, because in the end you'd expect, of course, UQ to be part of the story somewhere. Maybe roots of unity. I mean, there's a lot I don't understand about this stuff, but this at least seems to be one, piece of data that seems plausibly close to the truth and isn't really part of the standard way of viewing things. So that's why I want to sort of sell this approach and also try to write up something on it relatively quickly.
Yes, that sounds right. But as you say, the corresponding story, even in the much simpler case of Reshtik and Turayev, has not been written down. So
right.
It's a big ask to write it down here.
Well, the first thing I'm going to write is what happens when you decategorify twice, where it gets even simpler. So there's an answer. There is a fully extended 2-dimensional TQFT that plausibly arises as the sort of decategorification of this, or at least if such a thing made sense. I mean, but at that level, everything is rigorous, and you can say some nice things at that level, and then yeah, in what I write, I'll basically try to say whatever I can precisely about the 3D level, and just say, okay, this is my first, I guess, entree on this topic. But yeah, even at the 3D level, it is very subtle and not really in the literature, and probably related to some things it would be great to talk to you and your collaborators about, in fact. And then at the 4D level, it's just the first inklings of what could be going on. You have to go look in Lurie's higher algebra and sort of try to wrangle all the definitions into place. You can't just work with strict DG2 representations, right? Because if you're going to try to build in Heegaard Floer homology with these A infinity bimodules, that's not going to be strict DG. You're going to have homotopy all over the place. You already
Yep.
need very sophisticated constructions to deal with that.
Yeah, very nice. Well, I look forward to all of it.
Thanks. We'll see how long it takes. Hopefully I'll try to get some stuff out relatively quickly in the next few months. That's the plan.
Any other questions?
Hey, I have a like backing way up basic question. So
Mhm.
I guess you're trying to, oh, not in terms of slides, it's actually more about the further remarks. You're trying to
Okay.
basically just keep going, like we have Heegaard Floer bordered and then cornered and then to the point. But I guess topologically speaking, I can understand why like we'd want to have bordered, and I understand why we need cornered. In
Mhm.
what situation would you need the point? Like what sort of gluing situation would you actually want to be able to like tensor things together
Right.
at
Okay.
a
So
point?
right. What I would say is that it's almost that already in the cornered situation, you want to know about that. You want to know something about that. And for the following reason is that what does Heegaard Floer homology do? As an approach to Seiberg-Witten theory, let's say we want to define Heegaard Floer for 3 manifolds. Well, what we're going to do is say, I'm going to take my 3 manifold and I'm going to make a cut along a Heegaard surface. And I'm just going to use that to build a closed 3 manifold invariant. So a closed 3 manifold sort of comes with the Heegaard surface in some sense, at least if you want to define this theory. Okay. And so you can think of this, you make this ansatz that, okay, well, I think the surface should get assigned a Fukaya category of its symmetric product. And then applying that ansatz to Heegaard diagrams, then that gives you a definition of a theory. Now, okay, so that's just closed 3 manifolds. Now say you go to bordered. Well, one thing you could try to do is say, okay, now I'm going to generalize beyond just Heegaard decompositions, and I'm going to consider decompositions where I have any 3 manifold on top glued along a surface to any 3, not necessarily handle bodies. But in fact, that's not how bordered works. Bordered instead takes and makes another cut transverse to the Heegaard surface. So just like Heegaard Floer is more or less based on what would happen in dimension 2, bordered Floer is more or less based on what would happen in dimension 1, where you're going to consider this transverse cut really in terms of how it intersects the Heegaard surface. And so just the way I sort of think about it is just like ordinary Heegaard Floer is based on this ansatz about surface gets assigned certain Fukaya category. You can think of bordered, not even just cornered, but bordered Heegaard Floer as being based on an ansatz about what gets assigned to 1 manifolds. And I'm going to get increasingly less precise as I go down, but sort of what gets assigned to 1 manifolds is going to be something that looks like it has Strands diagrammatics. It's going to, these features like d over crossing equals 1, that sort of thing is going to be like that's sort of the ansatz for what Heegaard Floer assigns to a 1 manifold that underlies bordered. So then if you go one step below, if you continue this analogy, then it's also true that in cornered, still, you introduce yet another transverse cut, and you still have the Heegaard surface that's transverse to both your cuts. That's really like 3 cuts on a 3 manifold going down to points. And in fact, that's why you would see these corners in the sutured surfaces, that sort of thing. So what I would say is that to have a truly flexible and like fitting in with the notions of TQFTs defined for plane manifolds, whatever, if you want this perspective on Heegaard Floer, even down to the level of cornered, then you want to think about what gets assigned to a point, even though one-dimensional gluings are not so, there's not so many one manifolds I can glue, especially since I'm just talking about one manifolds and like plain one manifolds without decoration. So there's not so much I can build just in that plain set. Decorated setting is very different, but this setting, it's trying to see if Heegaard Floer could perhaps be viewed in this setting for plain manifolds. And yeah, I agree. It's less for applications of this to like gluing problems or something, and more for understanding how the cornered theory would work. And then correspondingly, the cornered theory, now you start moving upwards and talking about three-dimensional cobordisms. Heegaard, like this cornered theory should have a lot to say about defining Heegaard diagram bimodules from smaller ones by like extending by the identity. That sort of thing is what this is especially good at addressing. That's very difficult to do otherwise in Heegaard Floer. So that's the sort of applications, more or less indirect applications of this whole framework, which includes potentially this idea of extension to a point.
Can I
Okay,
give a,
thank you so much. Sorry, go ahead.
I mean, would it be reasonable to expect in the future some just be able to a way of getting Heegaard Floer homology from a triangulation of the three manifold that would be gluing, like that includes points?
Yeah, I would imagine that seems reasonable, although that's sort of, so if one could really get this fully extended stuff, then on general principles, yeah. But I think for me to speculate, like I sort of have already speculated about a lot of stuff, and I probably don't have that much more interesting to say about that than yes, that seems like something that would, but like maybe that on the other hand, maybe there's some no-go result that says actually you can't do X, Y, or Z. And then I wouldn't be so upset about that. I would just think, well, my understanding of this framework is, maybe my guesses are inaccurate in certain ways, and, you can, modify them and try to get it closer to the truth. But I would, yeah, that's something that I would expect as a ramification of a full elaboration of this framework.
Although I guess